Doug Kerns.
So this is Dr. Doug Kerns, who I'll introduce,
Yeah.
who I know locally. He actually hails from Chicago, got his doctorate here. Is it here at Caltech? Yeah. At Caltech. And is involved in the embedded world, but not the flight world. So this is for you to see what other people do.
Yeah, now for something completely different.
Yeah.
Although maybe not completely different. I'll try to persuade you it's not completely different, and we probably have a lot to learn. I'm actually blown away by all you. I'm Douglas Kerns. I'm with Cygenics Incorporated. We design and manufacture integrated circuit chips for things like avionics and medical devices. And I guess to properly disclose, I'm a significant shareholder in the company, so I have a financial interest in everything I'm about to describe. All right, what is intrafascicular space? Is it anything like outer space? Perhaps it is, but it's a medical term. It's the space between fibers in a muscle or a nerve or something. So a fascicle is a bundle of tissue fibers. All right, so if you're implanting a medical device, sometimes it will find itself in an intrafascicular space. It may find itself in other places, like a familiar medical implant device is a dental filling or a crown. It's there to fix your broken teeth, or a pacemaker there to fix your broken heart, at least in a superficial way. Artificial joints for broken bones, and of course engineers being what they are, we like to make things more complicated and interesting, so the complexity of medical devices is considerably more than just what's shown here, but I didn't have any other good pictures. I'm involved in developing things that have implanted electronic functions that are quite complex and interact with external devices for control or command. Okay. I'm in the electronics world. What's so great about integrated circuits, other than the fact that that's my business? Integrated circuits are the process of choice for manufacturing pretty much every active electronic device on the planet at this point. It's not all about microprocessors necessarily. The fabrication process is intrinsically made for mass producing things. You can very economically make huge numbers of electronic devices, whether it's single transistors or billion transistor chips, what have you. The other wonderful thing that everyone really likes, especially in this room, especially in the medical world, is that the devices you make are really small, microscopically small. They're very lightweight. They don't use very much electricity to do what they do. Now, about medical devices. First thing, do no harm. That would go against the grain of what medicine is all about. So we have a primary constraint on medical devices, safety, do no harm. Primary requirement is do some good. Otherwise, what would be the point? Well, what does that really mean when you're actually building a medical device? It's particularly an implanted medical electronic device. Well, we want to make sure that when you cut someone open to put something inside, you don't want to put something that's terribly big inside, because that's a huge invasion of your body's structure and function. Small object means a small cut, small hole to put it in, small object when you're done, minimal invasiveness. You'd also very much like to make sure once it's in there, it doesn't cause huge irritation. So the materials have to be biocompatible. And then finally, you'd like to make sure that the design of the device and the system are such that you don't really need to go back and do a lot of repair work or get other access to it, because then you'd have to be cutting someone open again to fix the thing you put in to fix what was wrong to begin with. And then the cure may be worse than the disease. If you have a complicated system that involves an implanted device with some external thing to control it or set it up, you now face the problem of communication protocols, operating protocols. How do you set these things up in order to be safe? Well, you need to limit the scope of autonomous machine action. So the implanted device should not actually be able to do very much, lest what it does be wrong, and maybe does a whole bunch of wrong things if it has a wide scope of activity. Another thing you need to do is limit the impact of autonomous machine actions.
Give me 1 second. Hello, is this Nate?
Yes, Nate.
Hey Nate, we just finished our seminar, okay?
Okay.
So this is the next one starting.
Oh, the first one's over?
Yeah, thank you. Bye.
We could rewind.
Sorry.
So we want to limit the scope of autonomous action. If the machine can take a whole bunch of different actions and something goes wrong, well, there's a whole bunch of different things that could go wrong. We'd like to limit that. We want to limit the impact of autonomous action. So any action that the machine takes should have some limited total impact in case it may actually be the wrong thing. We'd rather do a small bad thing than a big bad thing. I'm expecting some of these things are starting to look familiar to you people. And then finally, in terms of communication protocols, we want to make sure, okay, for example, handshaking, but in any case, the communication has to be a very high reliability protocol structure so that we can be sure to deliver correct commands when we actually execute a command. Well, okay, we're talking about complicated machines. Any given implanted device, it's got this electronic thing, and it's got some interface parts, and it's got some outside part. It's a giant pile of parts. If anything breaks, it has to stay safe. So we want to make sure that we do a complete safety audit, make sure that it remains safe under any given single point of failure. And best yet, we'd like to get, wherever possible, indications back to the operator, whoever has ultimate control of the machine, that the machine is currently correctly operating. So we want, good operating mode indicators that are positive. Don't just want to depend on red lights showing up if something goes wrong. Efficacy. In order to get past the FDA and in order to get past the patient who's facing the surgeon's knife, you'd like to assure them that your mission can be accomplished even if something sort of does go wrong. So in terms of communication, we want to make sure that the communication protocols allow for corrections of data errors. That's a very common problem. I'm sure you're all extremely familiar with that. In terms of hardware failures, we'd like to make sure that the design of the hardware system can sustain and continue operation even if part of it has failed or is damaged in some way. And in some cases, for multi-channel systems, that means we have to be able to shut down and disconnect individual channels from the rest of the system. All right. Here's an example of a real thing. Okay, I'll give you a long explanation of what this is about. It's a picture of someone's brain with a bunch of electrodes on top of it. Why would somebody want that? It turns out that in epilepsy, the seizures are caused by some piece of brain tissue malfunctioning, and that malfunction spreads as a wave of malfunction activity across the brain cortex. In extremely severe epilepsy cases, the cure for this is cut open the person's head and scoop out the offending piece of brain tissue. That's a really brutal cure. So what we'd really like to do is very tightly identify the offending piece as narrowly as possible and understand what's actually going to happen as a result of scooping that piece out. I mean, other than stopping the seizures, we're also going to scoop out your ability to wiggle your finger or see this quadrant of your visual field or something. We don't know. So this is an actual procedure that is done currently using hardwired electrode arrays that are put on people's brain surface, and they observe a seizure in action, identify the focal point, stimulate in the region of the focal point to discover what the functions are, and then proceed to go and do the surgery with full knowledge of what the functional deficits may be. So now we are, at Cygenics, we're working on a wireless version of this device that can be implanted in someone's brain and completely sealed up with no wires leading out. So we eliminate a major risk of infection. So this is a huge improvement in patient safety just by the structure of being a wireless device. Being wireless and being fairly complicated, now that we've done all that, we're facing this whole set of problems that I described earlier. So we've got a complicated electronic machine inside somebody's body. Once we launch it, it's inside somebody's skull. We lose physical access to the device. So, well, okay, in the very worst of all imaginable cases, we'd like this thing to become an inert mechanical object, sort of like a piercing or something. People don't usually pierce their heads, but you'd at least like it not to sit there and zap you randomly. For efficacy, the intended function of the device is to measure electrical signals and report them, and then to deliver stimulus pulses back to the person's brain on command, really to maintain efficacy in the face of all the things that could break. We'd like to have full observability and controllability of the electronics. So we have to include status reporting for all kinds of things, power supply and temperature of the die, and whether or not the package has been compromised and there's moisture leaking in, a whole set of operational variables. And then each channel of the electrode electronics has to be able to report its status, and we have to be able to disable them in order to preserve function of the rest of the array. Okay, we have a luxury you don't have. We can deliver power wirelessly, so we don't have to have a battery in the device. That eliminates a bunch of mass, it eliminates volume, and eliminates the need to replace batteries after some period of time. In addition, it also intrinsically limits how much electrical energy can be delivered. And in the worst case of something weird going wrong with the electronics, you can just take away the power supply hat and there's no more power and the device is inert. In our communication protocols, we ensure at most one stimulation pulse per command. That limits the total energy delivery even under a false command reception. And then, of course, we have things that are completely your normal world. We forward error correction in the encoding. We have handshake communication protocols to ensure that we receive a correct command before execution. The downlink has, again, a bunch of features that I'm expecting are probably at least vaguely similar to things that you run into in your world. We've got multiple communication bands. Each communication band has its own data rate constraints and its own power supply impact. So we can do things like dodging external interference. We can compensate for marginal power supply conditions on the implant. And it turns out that that's been a very, very useful feature in developing the system. Also, the communication protocol details include lots of error reporting of various levels of the decoding. Our error control coding is structured to allow us to correct at individual, my goodness, I've forgotten the terminology. Different sizes of bit packets have different kinds of error control coding attached to them. I'm sure you guys are very well familiar with that terminology, more than I am. I'm a transistor jockey. And then we also allow on-the-fly reprogramming of the packet structure, including the framing and the data payload contents. We often run into situations where, due to either interference or power supply circumstances, we have trouble synchronizing over a long packet or trouble picking up the synchronization at the beginning of a packet, so we can compensate for both of those kinds of problems. And then finally, inside the machine itself, this is where our world looks a lot simpler than yours, but it's rapidly heading in the direction of the world you live in. We're able to use a controller that's just a finite state machine, where we can actually exhaustively verify all possible states and verify that they lead to some initialization condition. It surely will happen eventually that a cosmic ray flips us randomly into some other state. We have to be able to find our way back. this is one key item where I think the medical device people can really learn from the flight software people, because we're rapidly reaching the point where a finite state machine controller isn't really an adequately powerful device to put into whatever the medical device function is. And then down at the analog hardware level, we have all kinds of fail-safe features. All the electrode interface wires are passively clamped with things that don't know anything at all about the rest of the system operation. Guarantee that we stay inside the water electrolysis voltage limit, so that no matter what else happens, you can't start making hydrogen bubbles. And we do, before actually deploying the device, it has to go through the single point failure analysis, and we have to guarantee that nothing can actually deliver power supply straight to the electrodes. That would be a considerable disaster in terms of not just hydrogen bubbles, but just heat. And as I mentioned before, we can disable or disconnect individual channels as necessary. So this is a device that's still under development. Don't actually have, at this point, anything I could say in terms of lessons learned. What I'm hoping is actually to come back in future years and learn more lessons from the flight software people. All right, can I take any questions?
Any questions? Yes.
I know nothing about the medical field, so I guess I'm just curious to know if the FDA levies. I mean, you're not actually delivering something to the FDA, but do you, maybe? But do you have standards applied to the work you do by, do you need to comply with standards like the IEEE or process standards from CMMI, those kinds of places, as part of the process of developing devices like this?
Yes, indeed. And standing in front of you at this instant, I can't quote you the numbers, but yeah, there are standards documents that apply to several different layers. The design process has to comply with a quality standard that involves proper specification of the requirements and engineering design and the whole design control flow and so on. It all ends up looking very familiar. The devices themselves have to comply to a bunch of safety standards, IEC 60602, Part 3. That's my world. Yes, there's a very rigorous set of standards, and they really come down to compiled common sense when you look at it very carefully.
I had a question about testing. I was wondering if you had some kind of hardware emulation of a brain that you would put this in, or would you use an animal or like a monkey or something, or just get volunteers?
Yeah, but that's actually part of the safety and FDA standard set includes what's called validation and verification. So we need to verify that the device we design actually meets its specified performance, and then validate it in some kind of realistic application. That, in the case of this device, is a dog brain. So there's actually a way to induce epileptic seizure centers. It's not something that's done to people typically, but one can do it to things like dogs and put the device on the dog's brain and verify that it actually does its intended function.
The other thing I wasn't quite sure of, are the sensors built onto that device, or there's something external that have a wireless interface?
Let's see if I can back up to the... How does one back up on this? Is it a page up? There we go.
There's like a network of sensors?
So what we've got is it's a flexible membrane with an array of metallic pads on it, and then wires back to an integrated circuit that connects to those metallic pads. So that combination constitutes basically a bunch of electrometers. It's measuring voltages at the brain surface in the various locations.
And that's the size of it compared to a penny, so it's rather large.
Yeah, I see chip sitting on a penny, and this is supposed to be actually
okay.
large.
The chip covers the date
Okay, now I see that. But the part on the left there is not relative to the size of the penny. Yeah.
Yeah, so the penny is roughly the same size scale as this entire object. The IC chip is a little silver rectangle up there.
Okay, thanks.
So do you learn anything? Does your chip have a capacity to learn what's going on inside, and are you able to reprogram based on the observations? Or contribute to neuroscience research or something like that?
No, this is back to the... sorry. Back to limiting the scope of machine activity in the implanted device. The implanted electronics are very simple. Their function is stripped down to the minimum possible set. And in this case, that set is measure and report electrical activity and to produce an electrical stimulation. It does nothing else besides that.
So does the electrical activity that you measure on a patient, can that be used to study what's happening with the patient outside of your chip?
Oh, it can indeed.
Can some neuroscience people look into that and then use that or something?
That, in fact, is part of the intended purpose globally of this type of device. They're doing it now using wired electrode arrays, but the wires have to come out through a hole in someone's skull for several weeks while they undergo this process.
Yeah.
So we're trying to improve that process.
Another thing, you said you supply power wirelessly.
Yes.
So is there any limit on the mobility of the person or anything like that, or they have to be?
The power transmission antenna is a coil it's about the size of my hand.
Oh, okay.
And they're wearing a yarmulke, basically.
Oh, okay. So it's a transmit power. Okay. Okay. Thank you.
In the spacecraft software world, some of the design issues or failure modes are figured out a priori as good ideas. Other ones are lessons learned from failures. And this might be a better discussion for after the thing over drinks. But I wonder if you have any comments about that. I'm just imagining how they found out that it was a bad idea to generate hydrogen bubbles inside the skull.
Yeah, there's a considerable history of implanted electrodes and electrode arrays in certainly in animals of various sorts, and actually to a large extent in people. So we do try to take lessons from all of that prior experience of things like hydrogen bubbles. Well, they change the pH and cause all kinds of tissue damage, and that's directly observable in lab experiments. Yeah, I mean, this is certainly it's an open-ended topic that we could, in fact, do something like a discussion over drinks. But there's a considerable history in medical devices and biological research that gets us to the point where we are here with this device.
Okay. Other questions? Yeah. Oh. Nope. You stay.
Being a hacker at heart, as soon as I hear communication, I hear spoofing. What sort of protections are there for some guy driving down the street setting off everybody's brain? Or not yet, maybe?
Yeah, not yet, but that's actually a topic of great concern, and the FDA has just issued a request for comments from medical device manufacturers on this very issue. Data security, both in and out, because any information that comes out of your brain as part of your medical record, that's your private information, not to mention your actual brain waves.
We will tie you into the cyber community shortly. Any other questions? Thank you very much.